Well, thank you, Rand, Zaven, Ando, Arsen, for having me. I'm here too often. Hopefully you don't have too much of me. I'll try to speak about different things all the time. So last few times where I was here, I was talking about my 5 years on bio and starting this field on non-contrastive joint predictive architectures that a lot of people still continue. I'm very happy about that. Like Jan is very excited about it and continues in that. But I kind of switched topics, or not completely switched, because I'm recently somehow combining the two. And I was lucky enough that I was part of the training, both Gemini's and Llama models. So when now you go to Llama, Gemini's, Google.com or AIMed.com, you will actually interact with some of the algorithms or some of the ideas that were used there. Actually, I forgot to. Yeah, so this was, no, there was a different slides, but yeah. Oh yes, here I tried to put Llama in the Yerevan, and this was good. And this I used a new feature in Google Slides. It was allowed, yeah. Not bad, not bad. It's getting better. Anyway, yes. So what I would like to, talk to you was like, is definitely a lot of collaborative work. A lot of people, my students, my postdocs, my colleagues from DeepMind, from Meta, from people that came from DeepMind to Meta with me and to my startup and other academics, all over the world that you may know. And they hopefully at some point come here too. And so if you want to read more about the work, so this is a sum of collection of papers. Some papers are just about to be submitted. So most of them you can find on my website on our archive, or just ask me about them. All right, so we will talk about definitely different things that I talked about 2 years ago, because this will be on Alignment. We have a lot of things to do, but the general, somehow like a general thing that I've been doing AI for like 27 years from 1999, and the only thing that I didn't change, because I did change, was kind of the approach to it. It's like, for me, it was always AI. It could be useful when we don't spend much time training it, right? So you don't want to have labeling, or and just doing something to model for be useful, right? You want it to kind of to be useful from the scratch. And another thing that I always was pushing is like, well, you should have the ability to AI learn from each other, right? And so that's why the common topic were always either self-supervised learning or self-play or game theory or something like that. And so this is also something that I've been trying to bring to LLMs, and somehow, and this is what we're going to talk about, right? So just to see where we are, so this is very old now, 2 years old, 3 years old, traditional recipe how we train, all the GPT models, very old, very old. But we didn't change much at the same time, first we go and download old internet, or we go to the Hinex Fine Web 2, and then we train all models on a continuation of the work, right, of the tokens, right? So at the end of this training, so we have the sentence, and we ask it to predict next word or next token, right? Then we have here at that point, that we like to call pre-training. We have the model that can complete the sentence. We start and it completes. It's somehow chatty, but it's useless because it doesn't do what we like it to do, right? So for it to be useful, we usually go to the second phase, and we part of which is this instruction fine-tuning. We would like to model to be conversational, after which we want to say, well, Michal says this, model says this, Michal says it, the model says it. This is just natural, but then, we would like the conversation to be useful. So we kind of change the data that we train. And so instead of just having the sentence and follow up the word, we actually said, well, this is for this sentence, we would like you to output this other sentence. And maybe we pay people, maybe we create the data set also artificially, but somehow the data sets change, right? So it's no longer the complete the sentence. It's like, for this is a good output. So very much you can call it, you can, like you can look at that as a child. At the beginning, it can complete your sentence. At the end, like it can imitate the parents. And then the last time, where we often called reinforcement learning or reinforcement learning with human feedback, reinforcement with fire feedback, offline reinforcement learning, and so on. We tried to somehow first go beyond what was trained. So not only imitate, you can see at a real human training, right? Like the kid learns, imitate the parents, and then hope, at some point maybe human became a scientist and can discover new things, right? Like hopefully, But we don't need everybody to do that anyway. And so one other things that we do before kind of going beyond is like we would like to also stir the models to be somehow useful. So since on this part, model was still all internet. Internet is not a nice place. If you go, under any, online forum in my country from Slovakia, first time it's just the slur words, and then it's racist. I hope, probably Armenia is better than this, but like in general, internet is not a nice place. And so like if we would complete model on Reddit, on 4chan or stuff, which we do, it will probably not be a good conversation partner. And this is what happens, right? Like and for example, if you have behind yourself a big company that wants to have some kind of, what's going on? You see, so it's already in the days, and somebody doesn't like it. Something. Important, like you don't want the model to be racist, sexist, you pretending it's a financial advisor or pretending to be doctor, who will be responsible for what's going on, right? I'm not doing that, maybe, but it's okay. It adds to the dynamics, and so like we also want to tune the model, and so practically what we do in this, for whatever in this last phase, we. Instead of, because we sometimes don't know how the right answer should be, so it's not sexist, it's not like doing something bad. What we actually do is that we take this model or some other models, maybe do multiple rollouts. So because the outputs are stochastic, we ask them, okay, complete the sentence, do the multiple completion, and then we ask people, usually, pay people. It could be hundreds of millions of dollars just for that part to see which one of the two or which one of these 10 was a better answer. Because it's somehow hard to say what would be the right answer. It's similar to say like, well, I don't know how I should drive a car, but like you can compare two driving styles and say this one is better, right? So the kind of like, this is one of the reasons why we, talk about different kinds of training, because like somehow input-output is different. So here, finishing the word, here, pairs of sentences, and here, preference between the two. And so this is, most of the people have been training that, and including when I was in DeepMind, and our first model was not Gemini, it was called Sparrow. So this was part of, and on top of that, we also have like 20 different models, exactly not the sexist, not racist, not financial, like 20 of those things that you don't want it to be, kind of complicated. And so this is still somehow prevailing technique. And so what I'm gonna spend until 11 here, I'm gonna try to convince you this is all bad, and you should do it the way I like it to do, okay? And this is something that help also us within the Gemini to get better results, and this is something that also I brought to Meta. And but before that, we need to have a kind of a reality check, what this reinforcement learning can do for us. So, from the past, 10 years of successes of reinforcement learning AlphaGo, or playing just Atari games, we had like something that would now be called tiny networks, but that we're still not allowed to say how big they are, but they're very small. And then we took 10 to the 10 training steps, like huge amount of steps, right? And then at the end, we have something that could like have a Mario brother go and jump and like collect apples or whatever it collects, right? A huge amount of steps, small networks. Now let's say, Llama 3 had 4 or 5 billion models. Gemini 4 is bigger. But at the end, the training steps, not for the pre-training, but the reinforcement learning training steps, the one that we're supposed to build and on new knowledge and improve, it's only like between 1,000 or million, or sometimes even hundreds for some tasks. So there's a huge proportion. So it's actually twice worse, right? So first, smaller networks, a lot of training, so probably we can get somewhere. Now, huge network, almost no training at the end, right? So just a reality check, we cannot expect that much more. Like here, pre-training is absolutely primordial because, you don't have the time, Well, it's nice to say, well, yes, if we train it eventually with that many steps, we could go somewhere, but we're not because it's just very expensive. And so we need to take the best out possible of these reinforcement learning training steps. And so let's now focus again on this part, right? So already since first version of ChatGPT, people realize that, well, asking humans to compare several pairs is not only expensive, let's say money would not be a problem, sometimes it's not. And it's time that is a problem, right? So instead of for each of the thing, and we want the model to be trained as fast as possible, right? Because there is a rush for being the first. And so instead of having for each model 2 outputs and asking humans, well, we just collect a lot of pairs. We pay millions or tens of hundreds millions, and then we train models to kind of generalize from humans, to kind of replace the humans. So once later, we don't need humans anymore and tell us which of these 2 is better, right? So it's very, very the simplest supervised learning. We collected data on the form, prompt, one output, the other output, and the human will tell this one is better. And at the end, we convert it to something that we call an ELO score. ELO score is something that's we use for chess, or for example, in ATP, in tennis ranking, right? So it just converts each of the player to the quality of play, right? So here we have prompt and output, and he said, well, for this prompt, this output has this ELO score, right? Let's say Kasparov has the best chess floor, and I don't know, Nadal retired. I know there's some good tennis players now that I don't know, and they have a good scores, right? So it's a very simple technique. It says that, well, ELO score is just a number that if I want to see, probability that you prefer, let's say this tennis player wins about this tennis player, it's a reward of the best one, of the ELO score of the best one minus the other one, sigmoid, right? Just to understand, we don't get lost here, because this is when I call game here is that the play is that I take the prompt and I have 2 outputs playing each other, either y or y prime is better. It's like 2 chess players play each other. So the play here, who gets the best completions to this prompt? Doesn't need to be 2. We can have the play. We can all play together. I give you prompt. Everybody gets possible completion, and there will be some god that decides this person has the best completion, and this wins, right? So this is the play. In this last set of LLM training, we're actually playing the games. And in my country, where or maybe better from Czech Republic, is we have this guy called Comenius, John Amos Comenius, that said, well, when we want kids to learn, we should make them play games so they don't think they're at school. I hope the school feels like play, but this is something that was always inspiring me, and this is something that I try to embody here. And so, the big change that I will ask to make, or that's what we're doing now, that we stop training the models in the way that we'll say, oh, this is the prompt, and this is the output, and this is the ELO score, and instead, we will train it differently. We say, this is the prompt. This is one output. This is another alternative output, and I'm going to ask the model, to train the model. So this is the reward model, to say, well, what's the probability that this one is better than this one? What's the preference of y over y prime, right? So I take the same data, same size of the model, same supervised learning, I just kind of change input and output, right? Like here, I just converted, pairs prompt y, prompt output to ELO score, and he will just, well, let's just forget, I don't want to learn ELO score, I will just directly try to learn preferences between the two, right? I didn't say, please ask me any question anytime, because I'll speak and I'll use all the time, and you will have no time to ask question at the end, so please interrupt me, just yell the question, or you can raise hand if you like. And I will use this time to drink. Is here this grill because like this is like the main kind of change what we're doing. All right. And why I'm doing this thing, right? Like so, you're working with ELO score is somehow assuming that humans' preferences are modeled by somehow a sigmoid. Maybe it's true, maybe it's bad, and I'll try to say like, well, why should we do that? In science, we often use assumptions. Like, for example, we calculate something with physics, we ignore the frictions. Why we do that? Because problems simplify, and then we can do something easier. Well, the question is like, does ELO score simplify something here? Yes, it's like there is a simple formula that explains how humans learn, but why we're just not learning it? Same data, same network, what did we simplify with using ELO score? It just looks nice because like we always use ELO score for AlphaGo, for chess, for tennis. It's a game. Why not? So I'll tell you why not. So we will just here assume that, well, we're just going to learn how humans make preferences, and we don't assume anything about these preferences. It's the only thing that I want. So on this prompt, how humans prefer prompt y to y prime is just this anti-symmetric. So if I prefer something 90% to other one, I prefer the other 10%. Nothing more. I will not require anything. And then I can just kind of decide what is the preference of all population. He said, I will say, well, if I'm preferring this output, this completion to this one for this prompt, that means practically, if I sample random humans from the population of Armenia, and then this human Z will prefer, every human has this function, how it prefers one from the other, it's deterministic. And then the thing is probability because I take expectation average over all humans in Armenia, right? And so then I can say once I can define how I prefer one completion to the other, I can define how the two outputs play, then I can make the models play. So like I said, well, I prefer, how much I prefer like the Llama 4 to Gemini 2.5, given on this prompt. I will take, well, let's randomly sample output from Gemini, then randomly sample from output from Llama 4, and then I ask, like, for this randomly sample output, what is the preference that average Armenian prefer that, right? And I will say, this is a probability of how much I prefer one model to the other. And so, I'm not going to continue much with those definitions. It's only to show that once we have this, what is probability of winning, then we can just ask something extremely simple. That will be our kind of the final question. Once we have this, what is probability of winning, then I can ask for Nash equilibrium. So coming back to something we already know. So ChatGPT, after this supervised fine-tuning, finds the model that we call SFT checkpoint, weights that are after the second phase, and this last reinforcement learning phase finds one model that's better than this model, right? By asking humans, we just change a little bit, reinforcement learning, fine-tuning model, we change it, but we find one models that humans would prefer to this one, including not sexes, not races, and maybe having better capabilities, right? And this is all good. Well, now, and we found one model, let's say the, GPT-5 post-train is better than GPT-5, after supervised fine-tuning on all possible prompts, right? Like we find one model is better than this one. Well, good, right? It's always good to have something better. But now, once we have this beautiful definition, we can ask, I don't want just one model that's better than this model. I want a model that's better than all possible models in the world. Why I should care about that this model is better than this one? Maybe this model is horrible. And so what does it tell me? But if I tell you this model is better than all possible models in the world, well, then now we're talking, right? And it's something very simple that we didn't need to invent it now. It was invented by Nash in 1960s, and he got a prize for it, obviously, deserved. So it's just, he defined, like Nash equilibrium is just go for the best, and he defined it like, oh, the model will be in the equilibria, so you keep playing between the models, which one is the best, and on equilibrium, so if we found the best, meaning that if I take my model that has zero exploitability gap, so it's like kind of the best possible, and if I compare to the other model, I cannot find any other model possible, right? So I'm looking for the best model, such that if I compare to the other model, so if I can take like the worst opponent, then my model still on average is better. This just means take the best. Take the model that if I compare to the other model is better than possible. So what we change now, according to the original ChatGPT, like how we started to train, for example, the first Gemini 1 and 1.5, was that we don't want to have one model that's better than pre-trained model. We want to have one model that's better than all possible models, right? Natural, somehow. And so now I'm going just to convince you, continuing convince you that this is a better goal. And why this goal is different than the previous goal? Because I said, well, yeah, it sounds natural, but maybe we also achieve it the old way. So, well, I'm going to skip that. I'm giving you 4 reasons why you should go for this new definition all the time. And smile. And stop doing this Bradley Terry, the ELO score models, right? I'll try to give an example for all 4 reasons. So human preferences are diverse, right? Not everybody is the same. And therefore, like the data sets that we're giving are diverse, right? I don't know anything about politics of Armenia, so US politics much simpler. There are Democrats and Republicans, in my typical example. And the thing is, like, if you go for Bradley Terry model, the traditional way of ChatGPT, like, let's say you have 50-50, data points in your, if your preferences, half people prefer Republicans, half people prefer Democrats, and you have just one person more from Republicans, then the Bradley Terry model is winner takes it all, so your final model will always give you a Republican answer because, it's winner takes it all. You want to satisfy the majority. And it's very fragile, so if you get 2 more data points that now are Democrat, you add it to data set, and you try to find the best possible fit, then everything just becomes Republican, because now it's winner takes all. So this is like extreme example, but actually, it's actually a good example because the typical example is much worse. Because imagine you have 100 different subpopulations, and one is just tiny bit bigger, then the whole model is trained just to, cater to this minority, which is slightly bigger than every other minority, right? Which is not something we want. I would like, if I have roughly 50-50 preferences, I want output a model that roughly gives me 100, like half of the time Republican answer, half of the time Democratic answer. Unless I want to have some autocratic regimes, and then you won't have a maybe different training style, right? So the Nash equilibrium will just kind of have this mixture policy that one time it satisfies one subpopulation, one times the other one, right? If there are 100 of them, it satisfies in a mixture all of them. The other things that it's just very limited expressivity, right? So so what ELO score does with preferences, it assigns every single player a number. So here, let's say for one specific prompt, this output has ELO, 10,000. This output has ELO 34. This is 4, right? And so you kind of see which output is better. But some of the preferences are not good. Like, let's say I play tennis. I'm better than Hrant. Hrant is better than Ando, and Ando is better than me. There is no number we can give to each of us, such that we can say like, oh, I just compare the number and higher number wins, because it's a circle, it's a triangle, right? And so ELO scores kind of say, I cannot have those triangles, I cannot have circles. The preference is linear, but the humans are not so simple, right? So this is another very old examples. You can have these kind of dice, that you have uniform 2, 4, 9. 1, 4, 6, and it's and you're rolling the dice and higher number wins. And if you compare two dice, first is better than second, second is better than third is bigger one, and it's exactly with 5 of 9 probabilities. And this is a recent paper, but by friend and some people from Mila and DeepMind that's kind of said, well, there is this. It's not just they're transitive; they're also no additive, because it requires how this difference should be. So if I like something, so it's kind of like, oh, I like I don't know, chocolate ice cream better than lemon ice cream, better than raspberry ice cream. That ELO model prescribes from these probabilities. I can exactly calculate. And while I could say that, okay, if I like chocolate more than lemon, more raspberry, I probably like chocolate more than raspberry, because humans are not that weird, well, hopefully. But I will definitely cannot prescribe the probability by some formula. And so this paper studied this in kind of real world games. Any questions? Yes, please. Thank you very much for the question. Yeah. No.
Yeah, we thought about that we are relying to human responses.
Yeah.
And I'm thinking that many people are being lazy sometimes, and they might choose randomly between, or always choose the first one just to continue and don't waste their times.
Exactly.
Have we any techniques to deal with it?
Yeah. So for example, if you are one of these person that for example, is being paid for stuff, right? You just wanted to have as many possible, you just click randomly because you just want more money, right? So how do you prevent this? So, simple thing is that, well, if you just do completely random things, then it's actually it's a noise, because you're just not helping much. So you could ignore that. But you could also be worse. I'm going to give bad data to my competitor, and I will actually say completely opposite, right? And so, this issue didn't come up with large language models. 20 years ago, I was creating models for hospitals. There were no deep learning or stuff, and even that we have to sign which doctor's technique is better than the other one, and we had to ask doctors to rate them, right? So there are techniques, to find, so the simple one is just you do voting. You ask for the same question multiple people, and you vote. And you hope there is no coordination between them, and you only take if the votes are kind of consistent. Let's say I would have a lot of money, and for each of the questions I would ask 100 random people, and I said, well, I will only take this an answer if 90 of these 100 say the same thing, and if it's less, I will say it's noise and it's hard to say, right? So there are people then all these companies, right? So if you are in one of these, if you're people like me, every week you get one of these companies pitching to you, buy my data, people from Search, Merkur, Turing, Labelbox, there are tons of companies that provide the data, and each of these companies will try to convince you they don't have this problem that they have, right? And they have different things, they have quality insurance, they randomly, look at the person, how they rate, they have automatic quality insurance to say, well, I will try, for some of them, they actually know the transfers. It's similar when you had Amazon Turk 15 years ago, some people just try to make the most money out of it, and they're kind of procedure. But it's not guaranteed, but these are the typical technique, averaging, voting, testing, quality insurance. And the best possible, and that's why the easiest and fastest progress in that field is that when you have these verifiable rewards, right? Some things, it's just not up to human preferences, right? Whether the answer of mathematical question is correct, that's not a preference, right? Hopefully, right, for now, like, we're still respecting science. And so, like, that's why, all the new reasoning models for code, whether one code runs faster than the other, so that's why it's much easier, because, like, we don't have the problem there, and that's why we can first automate it, and then trust the result. So that's we'll be seeing more and more progress this way, because, like, if you said, oh, what's the better Armenian poetry between this and this, maybe even you will not agree, right? Because it's just hard to decide. Any other question? Yes. Exactly, yeah. It's a probability, yeah. So I have this is two, I have two other reasons, but like there's a simple answer first, but then I'll take 5 more minutes about that. Is that, yes, it's a science probability, but it says this is exactly the probability, and the probability is assigned such a way that it respects the sigmoid of the different, right? So if I give reward 4 and the other has 3, then the probability is exactly sigmoid 5 minus 3. But the real probability could be different. It's just like I'm just fitting a very small number of parameters to, meaning for each of the answer I get one parameter. You can imagine that you have each of, let's say each of the people on the table. This person wins with this probability, this probability with this one. Well, actually, I have this table here. I just skipped it, right? So like this is the real data. But ELO score actually represent all these tables with giving ELO score, one score to each of them. And so it's assumption, right? So it's a small number of parameters, which is the best possible representation by small numbers. So from quadratic numbers, you have only linear numbers. So you save. So for example, here, if ELO score for one is 0 and another is log 9 is log 2, you get exactly. So 3 numbers is easier to represent than whole matrix. What I say, and that's why we often use ELO score for all the things. But now, if I have the huge 400 billion network, why I should make it learn these numbers, which is less data, than this number, which is more data. So that's kind of like the main thing. Yeah, there's another question.
The fact that different people have different preferences brings into mind the recommendational system. Probably you can build some embedding of the person according to charts and suggest some, not maybe more ethical, not different opinion, not different way of use, but just formats how people.
Absolutely, yeah.
Do you know any works about such kind?
Oh yeah, I mean, like, so there's tons of work that just study, okay, well, I just train it on this population, it's very, it's exactly what you would expect, culture preferences are exhibited and sometimes magnified, because oftentimes, so one example why the hallucinations happen, there are many of the reasons, but why the magnification of the preferences often happens that, at the end we train models to give a preference. I like this one more. We don't even give it actually option, I don't know, oftentimes. Sometimes we do, sometimes we do, but oftentimes in the training, we just say, well, you could say I don't know, but then you don't get anything. But if you randomly choose the answer, maybe what you want, you maybe get rewarded. And so models learn to actually make the answer, even that, absent from, humans often say, well, I don't know, or I prefer not to answer, because you're not punished for not answering, but models are punished for not answering. So this is one of the things where one of the million reasons that you get these magnified references. So sometimes it's enough to have very little, let's say, opinionated data, and you see it much more. That's why the models are very confident, right? Like GPT-5 is always confident about something. And so, it's not right. Oh, sorry. But in the end, it's confidence about something. And this is one of the things where it's stemming from that. Any other questions? I like more questions than talking. Okay, there will be opportunity. So the third reason, and I will not go to distribution, I'll try to explain it. It's the way how the ELO scores are calculated is very sensitive. It's defined based on sampling distribution, right? Like ELO score for chess, it's calculated. I take all the parties, all the plays of chess people together. I calculate ELO scores, by simple formula. But let's say I'm a boy from Armenia, from a small village. I was 2 months ago teaching in Tascador, if I can pronounce correct. Let's say I'm from there, and I'm like the best chess player there, right? And like I beat everybody there. And then if I go to Yerevan, I suddenly lose, right? But let's say I would never go to Yerevan because I'm just afraid to meet somebody which is good in chess play. So I stay and I just play with my little sister and her brother, right? And my ELO score will go super high because I will never play with anybody else, right? I get even more extreme. Let's say I'm like the worst chess player I'm the second worst chess player in the world, but there is somebody worse than me, that's Hrant. He's even worse. And I want to have big ELO score. And so if I only play with him, I win. And I have even higher score as Kasparov because I will be afraid to play somebody else because I could lose, right? And so I could actually artificially blow down my ELO score just by playing with people worse than me. In real life, if I go, oh, I'm the best chess player, make me play in Olympiad, people, well, first like beat Kasparov or whoever, and then maybe your score will be adjusted. But it's really true that you can just make bigger score. And that's actually the problem, problem in comparing those scores between each other. Let's say each of us here, we align our preferences, we play with each other, and there are people in the other room, the room B, have their preference. We never play with the people from room B. Then our ELO score will be uncomparable. Maybe, even the best person here will be worse than worst person there, but since they never play, we don't know. And you could say, oh, this is very contrived example, it doesn't happen. Yes, in chess it doesn't happen because once you're getting good, they make you play with somebody that everybody thinks they're good. But how are LLMs? How many plays we do? So for each prompt, we give it to Scale or Search or whatever, not Scale because now it's bought by Meta. We gave it to some of these companies, and one person rates, so the game is only played once. And so you have only one comparison between the prompts. You don't have many comparisons. So ELO score calculated with one sample is very bad. Then we're hoping deep networks train it, but it's just very bad to make this comparison. And so that's why the sampling distribution matter, because yes, if I actually make everybody play with everybody, meaning if I would compare for each prompt, each completion, then the ELO scores will be nicely calibrated because I would have a lot of data, but I don't have a lot of data. And that's what considered problems in, for example, in offline, maybe some of you know the offline algorithm of DPO, that's like offline version of that deteriorates because of the problem. I don't have enough things. I don't even have comparison. Another way how you can see this mathematically, if you don't like my chess with Hrant comparison, is like if you have a sigmoid, the highest value of the sigmoid is it's like, well, between 0, how you scale it, it's between -1 and 1, or between 0 and 1, right? And if you have only one comparison in that definition, sigmoid winner minus loser, if you want to get this person always wins because you have only one sample, when is sigmoid equal to 1? Well, if the reward is infinity. So that's actually your implicit trying to learn infinity, and deep learning models, I have very difficulty to learn infinity, so there we have a lot of tricks, gradient clipping to avoid that, right? And so here I'm kind of, arguing for fixing this problem in the beginning, that you don't need a lot of fixes, clipping and trunking and gradient normalization. You do it for other things, but not for this one. But like the people in Meta and DeMai, they didn't give a shit about my comparison with mathematical. The only way how you compare the management is just like it gives better results, right? So we did for Google DeepMind, right? We just say, well, it just fits better. We did it like the simplest machine learning example. You take your data, right? Your preferences, prompt output, which one is winner. You take 70% train test split. On 70%, you train two models, one with ELO scores, ones with preference scores, just between 0 and 1. And then you test on the 30%, what are the preference scores there, right? And the ones with preference fits better, few percent better, but it matters quite a lot. And that's what convinced people. It's not even that surprising trends, but right, the data comes in 0, 1. So if you transform it through some nonlinear function, the ELO score, and then you try to predict what it came from, well, you lose. I mean, there is a theorem for that. It's called data processing inequality. You probably learned it in school. I mean, if you cannot gain more information you can only lose confirmation if you transport like the transfer data through a function. So I have 10 minutes left. I just learned. So, but that's very good because like Pierre has a talk. And so hopefully now I convince you that I want to train models that models will be better than all possible models. And now it's just a question, how do we get there? And so this is the story that I'll tell about the games trees and the self-improvement, the stuff that I like. And it took actually quite some time. It actually took 10 years of research to get there, right? And it comes back to solving imperfect information games. And so imperfect information means like if it doesn't ring, you just think poker. Means imperfect information because I don't see the cards of my opponent in poker. For example, in Go, in chess, I see the board and I know everything about the game. I don't see what is in the head of my opponent, but I see everything. I have full information, like full information games, and these are imperfect information games. So like games like Stratego or poker, or whenever you don't see anything, you don't have a full information. And this is just a photo of Phil Nice because he looks nice. And he kind of started, these games by self-play already, 60s is long to 40, 60 years ago, 65 years ago, and almost all research on this imperfect information, all perfect information, was done by drawing the trees, right? So this is the tree from Stratego, or no, this is from AlphaGo, right? You have, and why are we drawing trees? Because, I play a Go, like I play under place, and at the end somebody wins, and I know somebody wins, and then I have some algorithm that figure out what should play, right? It's kind of natural that we draw trees. And the same thing for poker, right? Oh, I play, like Hrant could have this card, or this card, or this card. In this case, I would do this. In this case, I could do this. Let's find the best possible solution. Oh, in the worst case, he could have done that. And, we have optimal algorithms for all of these possible, right? The thing is that once the game gets too big, this just doesn't work. There's no problem with algorithm. Algorithms are perfect, optimal. You cannot do better. Monte Carlo tree search, algorithms of trees, we understand them all, and we could not better. The things like when you get to the games like Stratego, you have 10 to the 1,000 possibilities. It doesn't fit the memory. And in the language model, the tree is like, okay, I have a first token and second token, third token, and possibly unlimited text. Gemini 1 had 4,000 tokens. Gemini 3 has, 2,000, 20,000 tokens. So each time I have 220,000 possibilities. So this is a very, very, very big tree. And if the text is possibly infinite, well, it doesn't just fit the memory. So I cannot draw a whole tree and find a perfect game, even if I could. It just doesn't matter, right? And so all the things that we kind of practically invented in machine learning in last 10 years is this distributed computation that put us very far. It's just, we have this replay buffer, right? We did the same thing with Atari games, same thing with AlphaGo, same thing with large language models. We buy a lot of GPUs or TPUs. We put them in the data center next to Sevan. I heard there is one coming. And we just, we have, for example, AlphaGo, we let them play games. And Or in LLMs, we have them like outputting the tokens for the prompts, And then while we take them, we put them in this replay buffer, because we cannot store everything in tree, so there is like a kind of database in replay buffer. And there is just often here, like a CPU, because CPU can do computation, takes few things from the replay buffer, updates, well, gradient descent updates the model, gets better results, and then we ship the new model, and we have like 100,000 GPUs to output replay buffer, and we do this on all parallel and asynchronously, and that's how we're able to scale. No trees, right? This works. But the question was, we didn't have algorithm for imperfect information games using replay buffer. And that's what we started to do 10 years ago. And so I have a lot of times, we had to have a big recipe. There was lossless estimate, regularizer, balancing, and this magic sauce that I'll talk to you about. So I started to work on it in 2014 with some students. And I came up with something called implicit exploration, which was a very simple thing, like extremely trivial thing. Like you will see how trivial that you will try to do the same. So the implicit exploration was something that I'm trying to estimate like reward or the loss, and I don't always try this option. So I try it sometimes, and then I divide it with probability of trying it, right? Like I only once in 10,000 times I try this move or this advertisement. So, but I need to divide it by 1 over 10,000, right? And so I estimate how good it is. And the thing is that these numbers, if I trade one, is very small, and so the fraction explode. This is not good for computers, right? And so like the simple idea that I had, well, I just add a small number to bias it. It biases a little bit, and so it kind of implicitly explores because it pretends it's slightly better. It increases the value of this fraction, but it doesn't explode. And so I made this funny slide like a year ago for myself. And I realized that all of my contribution to all my 27 years of research was just whenever I saw the fraction, I just add small numbers. You can see it all the time, and it's sometimes like the fractional difference. So this is the only thing I brought to science. So it's very easy to improve something in AI. And so like if I ever die, it's like I kind of say like Michal, Valko died in 2000. Whenever I say a fraction, this will be written on my tomb, when I die. Please do it, Like nothing else. And so this is actually what we did in 2024. And this took 5 minutes. 5 minutes, and then I'm making it still from my questions. Yes, and there was multiple people that continue, like people from NYU, people from DeepMind, people try to solve a method. This is from Michael Jordan group. They try to, and from Emation. Then we started working on it again for the games like Stratego and DeepMind, and he found algorithms that was not using the trees, it was not using the trees, but it was not optimal. It was square root of number of states away from optimal. But if number of states is 10,000, even under the square root is very big number. So we back to root during the time, but we still announce it as a DeepMind that we made huge progress. It's very important. So some people from from Mike Jordan group said like, if you just draw 3 once, you get optimal. And then this also method was used in Stratego, which is one of the algorithms that DeepMind. But we got back to work because we wanted to have something optimal. And so the thing was that we were just thinking, if we look at the 3 once, we will know the optimal algorithm, right? We knew that, not from us, but from Mike Jordan, Bailong, Shijin group. But the thing is, we cannot draw in 3 wise, it's huge. And so we had this idea that, if the opponent is on Nash equilibrium, it's optimal, so he needs to know the 3. So he said, well, if the optimal, let's pretend the adversary is optimal, so he needs to know the set. So if we copy, if we kind of observe how he acts, from here we can estimate the 3. And so we build this idea that I have done time to explain more. So instead of building the 3, we observe our opponent and try to guess, because we assume he knows the 3, because he's optimal, right? And so we were guessing the games from the moves of the opponent. And that we saw the problem, them is went and congratulate us. We won a Best Paper Award in ICML 2023, the one in Hawaii. And then we finally went to what we wanted for, solving Nash equilibrium, because Nash equilibrium is the game. because the only thing that we needed to have, well, we have the game for this prompt find the better completion, we'll just solve this game. And so the second part of the talk is about kind of solve the game, but it's very easy because now we have an algorithm. And so the algorithm is very simple. First, we just train this preference model that we spoke first time of the, we train the model prompt, input, output, probability, and then we apply our algorithm to find, the best possible, to solve Nash equilibrium, right? And the Nash equilibrium was actually already, we could even actually think that, well, but didn't Nash solve Nash equilibrium? And so here he did. This is his algorithm, and there's nothing wrong with it, actually. So the Nash said, well, you want to solve Nash equilibrium, human preferred answer of the other one. Well, you start from the base policy, from supervised fine-tuning policy. You find one model that's better than this one. So actually, Nash actually find how to train ChatGPT in 1960s. So this step is train ChatGPT. That he didn't stop there. He said, well, you have ChatGPT, you have better version, and then you combine the two and you find something better than these two. Then you combine the three, find better until the completion, right? And so we could have used this Nash algorithm, but like each of these models is 400 billion parameters, it doesn't fit in the memory. So that's why we use this algorithm for which we get this best paper work, like this based on mirror descent that we will not talk about, but Pierre will have an even better version of it. And I'll just kind of summarize it because this is, the theory also didn't matter in the release of model. But I will just say that this is one of our algorithms called mirror descent. It's just a big table. And the only thing, so here we do different way of training models. So this is like RLHF. This is how ChatGPT trains the model. These are all possible alternatives. And here I compare how much is one model better than this one. So of course on diagonal we have 50% because you compare yourself to yourself. And if you compare ChatGPT to supervised fine-tuning model, well, it's 99% of humans prefer ChatGPT over supervised fine-tuning, which is what it's training for. And if you look at our model, well, our model, is only compared to the supervised fine-tuning only 98%. So it's actually worse than ChatGPT if you compare it to supervised fine-tuning. But look at ChatGPT. If you compare to supervised fine-tuning model, which is what it was trained for, you get 99%. But if you compare to something else, well, sometimes better, sometimes it's worse. It's just, it was only trained to beat the other model. It was not trained to beat other possible models that we didn't see. However, if you get our model, sometimes with 98, sometimes 59, but it's always better than 1/2. So it's always better than other models, and which is what we want to have, right? We want a model that's better than us. So this convinces people to use this kind of method. And if you want to do this method faster, so today you have opportunity to, first public presentation of how to train this model by Pierre at 3 p.m. in this data fest here, right here in Armenia. You'll see how actually you can accelerate the speed of the training all the way. So please be here somewhere, maybe in this room or maybe other room, but it's at 3 to 3 p.m. Thank you very much.
Thank you. So you said that these things, your examples were on Palm 2.
Yes, because
it
we
was
could not
like
publish the one on Gemini because this was forbidden.
I see, but my point is that is this somewhere in production? I didn't get that right.
No, so like the one that we had production, we used in Gemini, right? Like, so it's the only thing where we were allowed to publish was in Palm 2 because that's, nobody, at some point, nobody was able to publish anything from Gemini, at least before the Gemini paper comes out.
Yeah, so these ideas exist in Gemini now.
Yes. So like so in Gemini right now, like you have like, well, you can read the latest report. In many models, people now combine both online and offline learning, and in these ideas is mostly used right now. For example, in Gemini, if maybe you remember this hiccup when like the model was, not very good, where it was having like the like black Nazis and stuff, so one of the things was fixed by some of these ideas. And And in a lot of people, including Gemini, like using both combination of online and offline reinforcement learning, because for something it's better to this one and something is better to this one. And so this is online version of the game theory. We have offline version that we call IPO, like which is equivalent to DPO. DPO is something that is based on this Bradley-Terry or ELO score. IPO is using this game theory. And so this was already used in the first release of Gemini, for example, fixing the problems. Yeah, indeed, yeah.
I see.
And it's on Hugging Face implemented. So please download it by TRL, by 4 people from Hugging Face that I thank. Yeah.
Amazing. Okay, I think we should stop here due to lack of time, and Michal is here today, so you can ask questions during coffee breaks and during after party. So let's thank Michal again, and